In this video, we will learn how to use pKa numbers to quantify acid strength. What this will do is this will help us be able to determine how a reaction proceeds and allow us to draw the correct mechanistic arrows. If you think back to resonance, where arrows were a big deal, arrows will be a big deal here. And the foundation of drawing correct acid-base mechanistic arrows is important because when we get to Unit 5, where we cover many types of organic reactions, we'll have 40 or 50 types of arrows that we'll need to be able to draw. And that sounds overwhelming, but if we get the foundation down here, there's just very small tweaks that you would use for each of them. Okay. So we're going to cover notes 4 and 5 in this video. For strong acids, the reactions lie far to the right. That means we produce a lot of product. What are the products in an acid-base reaction? Well, for strong acids, we're going to produce H plus and conjugate base, which we can abbreviate CB. Whereas for weak acids, we're going to form very little product. Okay, mathematically speaking, if we had strong acids, the Ka would be large. From notes 2, we said that if we are product favored, we would produce a lot of product and products in our numerator for our K value, so that would make K large. Whereas on the flip side of that, if we have weak acids, the Ka would be small because we're not producing very many products and our numerator would be fairly small. If we have a large Ka, we take the negative log of that. Negative log of Ka equals this thing called pKa, which you may have heard about before. And mathematically, when you take the negative log of a large number, that's going to make the pKa small. Where if I have a small number and I take the negative log of it, that will make the pKa large. So what's important to know is with pKas, the smaller the number, the stronger the acid. Okay? So what I need you to do is I need you to go online. You may already have it printed out. You may want to pause the video and get this printed out or look at it on your phone, computer, whatever. You need to have this in front of you, okay? We're going to have a pKa table, and you'd be given this on any sort of test. If you take organic chemistry in college, you'd have to memorize this. So what I'm going to do is I'm going to pull this up, and I'm going to show you what I'm looking at. And so I've got these pKa tables. And so what I want to do is I want to think about functional groups. Functional groups, very important in organic chemistry. Here I see an alcohol group, and you may say, oh, alcohol groups, I see that on here, and that has a pKa of 16, but that's a neutral alcohol group. So maybe something like this. This red H has a pKa of 16. What about an alcohol group that has a positive charge? Looking here, what I can find is its closest similarity, and that would be the hydronium ion. That would be an OH group that has a positive charge, and that has a pKa of negative 1.74. You are welcome to use negative 1.74, but what I will do, because negative 1.74 is the exact pKa of hydronium, and this is not hydronium, I am going to say that this pKa is about just negative 2. We'll just round it to the closest whole number. Okay? Now, you may be wondering, what about all the other hydrogens on here? Well, not all hydrogens are very acidic, okay? Actually, here we have a methyl group, so that has H, H, and H. And if we think about alkanes, we have those at the very top. Those are the least acidic hydrogens, and those pKa is 50. That pKa for those H's are 50. You may be thinking, okay, if I have my calculator, I can take 50 minus 16, and I can say 34 times less acidic, and you're wrong. pKas are based on a negative log system, so it's actually 10 to the 34 times less acidic. So billions upon billions upon billions, just numbers that are hard to even comprehend. Okay, so these H's are not going to be plucked off. Okay, you may say, okay, here, these H's, those are alkane H's, and I say close, so they're not 50. These are actually ketonic hydrogens, and if we look at ketonic hydrogens here, they have a pKa of 20, so this pKa is 20. If we think about why, we'll learn that after a couple more notes. But if I pluck off one of those H's, we'll put a negative there because the electrons will go back to that carbon. And then I have resonance, and if you can create resonance after you remove a hydrogen, that will tend to make that hydrogen more acidic. Okay, same thing here. This H, this is going to be pKa of 50. But in reality, it's probably a little bit lower than 50 because what it forms is something that has resonance, okay? But pKa of 50 is what we would say. If we had these H's, that would be an alkene, and alkenes actually have pKa's of 45. We're going to learn that double bonds are going to be a little bit more acidic than single bonds, and then triple bonds are way more acidic than double bonds even. Okay, so what I'm going to do is I want to find the most acidic proton here. In this first one, I see a triple bond, and I might be thinking alkyne, and that's not a bad thought. However, there's no H's actually on either of these carbons, and so I have to go to the next carbon. This would be 50 because that's just an alkane. H2 is on here. That's just hydrogen. That would be a pKa of 35. Here we have an amine group, but it's a positively charged amine. And that's going to be a lot different. So if I look here, a neutral NH group, such as ammonia, that's going to be pKa of 38. But if I have an NH group that has a positive N, that's going to actually be 10.64, which we could say is actually about 11. Here we have an alcohol group. Alcohol groups, I just will know that as 16. Oops, and I put that in the wrong spot. Sorry about that. Here I have an alcohol group, but it has a positive charge, and so we're going to think about hydronium ions for that. That would be -2. In this next one, we have an NH, or actually we just have an N group, but notice there's no H, okay? So that's not, there's no H on that amine, so we'll actually have to look at the next carbon, and so this pK would actually be 50. Here, no major functional groups besides alkanes, so we would say 50 as well. HBr, that's specifically on here. That pKa would be -8. Okay, and one thing that's kind of interesting, when you go to college and you have to memorize these, you'd find chlorine on your periodic table, and then underneath chlorine is bromine, and then underneath bromine is iodine. This is just from the periodic table, the halogens. Chlorine's -7, and chlorine's atomic number is 17, so those 7s are kind of not hard to memorize. Bromine's -8 and iodine's -9. So when I was in college, that was sort of a clever way that I used to memorize those. But like I said, on the test, you will be able to use this pKa table. Okay, it'll be the last page on your test. A positively charged alcohol, -2. This one, you might say, oh, alcohol 16, but that's actually wrong. This is something called phenol, and phenol specifically has a pKa of 9.95, which I would say is 10. Okay, here we have an amide. We don't see amides all too often, but amides actually have pKa's of about 8. Here we have an alkene, alkene, we have 45. Here we have a nitrogen. Again, no hydrogen, so we'll do one of these. What I would like you to do is pause the video, come up with the rest of these. There's a couple that might be a little tricky. I'm going to go through them here quickly. This is a ketonic hydrogen. This is 20. Positive alcohol group, -2. Water is the only one I need you to have exact, and that would be 15.7. Here, this would be 50. Here, this would be about 11. Okay, here, this one would be 38 because it's neutral. This one would be HX. X means halogen in chemistry. You may have known that, but so this could be -7 through -9. NaH, we have H+, that's not on our list, and we have, or actually I'm wrong. We have Na+ and H-. This is actually a base, okay? Anything with sodium out in front will be a base. So that one you can just put an X through. We got 50, we got 16, we add double bonds, that creates phenol. This will be 10, this will be 45, double bonds. Here we have no H's on this, okay? So that'll be 50, where we add a terminal alkyne, okay? Those are the only kind that we can have a pKa of 25. Here we have an ether, but no H on that O, so this will be 50, and then a positive alcohol will be -2. Okay, now notes 5, and I can open up our pKa table later if we need it, is what we're going to do a lot of in this unit. So you want to try to get this down. You may have to rewatch this video. So how do we know when a reaction will react with a specific base? Just because you can write it down on paper doesn't mean it actually happens. So what we need to find is spontaneous reactions, okay? Relative acid strength will be used to figure out pKa values, and equilibrium will always favor the weaker acid. Okay, the weaker acid will be the acid with the larger pKa. Okay. So, if I look here, we have a carboxylic acid. Carboxylic acids, if I look at my pKa table, have a pKa, I believe, I'm just going to verify, like not negative, but about 5-ish. So this has a pKa about 5. Water, the only pKa I need you to have memorized, is 15.7. So we will lie to the right because we form the higher pKa. So with acid-base reactions, you will need to know how to provide products. We'll be able to do that. It's very important that we draw correct mechanistic arrows, okay? That's where I'm going to tell you right now, that's where most students mess up. We're going to identify acids and bases. We will identify conjugate acids and bases. We'll get the pKa so we know which way the equilibrium lies, and then we'll be able to estimate the equilibrium constant. I know I'm throwing a lot of information at you right now, but on the back of your periodic table, you have a formula that says 10 to the conjugate acid pKa minus the acid pKa. That will give you your K value for the reaction. Okay, so we both have H's here, so what we need to do is label pKa's. The substance with the lower pKa will behave as an acid. And so if I think about this, this is not water, but this is ethanol. This has a pKa of 15.7. We have ammonia. This has a pKa of 38. Therefore, this will be acid, and I will use its pKa value. I'm going to erase the pKa of what's going to be my base here because pKa's are only for acids. And I'm going to draw lone pairs of electrons. Bases are required to have a lone pair of electron because the lone pairs of electrons are what forms or what allows the reaction to proceed. These lone pairs of electrons will come in. They will take an H, but all that it really wants is the H plus, okay, because the electrons are the ones initiating this reaction, and so the electrons in that bond will go back to its adjacent atom. So we have something that looks like this. Oxygen has gained electrons, so it will be negatively charged, plus we have NH2, and then we have a second H attached, and that will give nitrogen a positive charge because it gained H plus. Looking at our reaction, if NH3 was our base, this will be our conjugate acid, and this will be our conjugate base. For acids, whether it's conjugate or just your acid, we care about the pKas. We look at the pKa table, and the pKa of ammonium, which is NH4 plus 1, is about 9. So we form, if this reaction proceeds, we form a reaction that has a stronger acid, or an acid with a lower pKa. So I can say 10 to, and I'm just going to copy and paste. That would be smart of me. Okay, we're going to take 10 to the 9th minus 15.7. We get 10 to the minus 6.7. This will be called reactant favored. You could justify this a couple ways. I would say one way is that K is less than 1. Also, we formed a stronger acid, which is unfavorable. If you want to correct your arrows, what you could do is ignore these, and we would say some of the products are formed, but we mainly form reactants. Okay, let's look at the second one. One thing we're going to see a lot in acid-base reactions, and I've already said it earlier in this video, anything with sodium is going to be a base. That is because sodium is always going to be positively charged. It is what's called a spectator ion, and whatever's next to sodium has to be negatively charged. If something's negatively charged, it is a good clue that you have a base. Okay. So because I know that, this will have to be my acid. pKa of water is 15.7. And actually, as I look up, you may have caught this. This should not be 15.7. That's not exactly water. This should be 16 because it's an alcohol group. It's not going to change anything except our math. 9 minus 16 instead will be -7. So I apologize about that. pKa here, though, is 15.7 because we have water. Here, the negative charge on nitrogen, and if you want to draw in the lone pairs of electrons here. So there's two ways to draw this. You could draw it like this, or what we'll get used to is not even drawing in the lone pairs and just taking the negative charge and going like that. We're going to get oxygen with a negative charge plus NH2 with another N on it. And what's really strange here is we don't care about the sodium. I mean, you could leave it off if you wanted to. Sodium's what's called a spectator ion. Just wherever the negative charge ends up, that's where sodium will be. So sodium actually goes with hydroxide here, and we get sodium hydroxide. This will be base. This will be conjugate base. This will be conjugate acid. This pKa is 38. 10 to the 38 minus 15.7 gives us 10 to the 22.3. K is greater than 1, thus product favored. You could also justify this by saying we form a weaker acid, which is favorable. So I'll copy and paste this, just alter this briefly. Okay, this will take probably 10 or 15 practice problems until you get this down, so just be patient with yourself. Here, I see another sodium, and so I know that sodium's positive. This will be negative. We'll come in, we'll take an H, give the electrons back to the adjacent atom. We get H3C, C, and then H negative plus H2, and we have Na plus. That goes wherever the negative is. Because we have something with a negative, this will be base. This will be acid. This pKa is 50. This pKa for my conjugate acid is 35. We'll take 10 to the 35 minus 50. We get 10 to the minus 15. This is one quadrillionth, I believe. So K is less than 1. So this is going to be reactant favored. We formed a stronger acid, which would be unfavorable. Okay, same thing here. We have a negative charge. I want you to think about this as an H going out there. I know that's sort of annoying. If you're not going to draw the bond, you just need to make sure you draw an arrow that's pretty good here. It appears that I'm going extremely fast, I would imagine, but that is because I've done this and it just becomes very repetitive. And so that's where you want to get. This is acid. pKa equals 16. This is base. This is conjugate base. This is conjugate acid. Conjugate acid is pKa of 10 because that's phenol. So we'll take 10 to the 16 minus 10. Or actually, I got that backwards. Conjugate acid minus acid. 10 to the minus 6. This is going to be reactant favored. And same reasoning. We formed a stronger acid, which is just not going to be favored. Okay. Same thing. I see a positive. I see a negative. I want you to go ahead and try this on your own. Pause the video, and then you can check. Okay, now these questions, you may need to take a break before you get to these. These are some tough questions. We want to calculate the equilibrium constant, K. We'll do that. We want to determine if the reaction proceeds in the forward or reverse direction, so we'll circle the direction the reaction mainly goes in. And we want to have correct arrows. We'll label things as acid, base, conjugate base. I'm going to do a couple of these. One thing to note is that this is not in Q. I don't know how I typed a Q. Maybe A and Q are close to each other on the keyboard, but this is in A. Okay, so we're seeing sodium a lot. Sodium is positive. So whatever's next to sodium will be negative. This, whenever you have sodium, the thing with sodium, the thing with potassium, the thing with any alkali metal cation tends to be sodium. You could have potassium, but probably 90% of the time it's sodium. That will be your base, okay? So this is base. This is acid. This pKa, we have a terminal alkyne, so this will be 25. We go and we pluck off that H. Those electrons go back to the adjacent carbon. So we're going to get C, that carbon, this guy, has a negative charge now, plus HBr. That'll be our conjugate acid. This is conjugate base. Sodium follows the negative charge wherever it ends up. And this conjugate acid pKa equals pretty low. It's 10 to the minus 8. So I can already tell you we're going to go to the left. We're never going to form a stronger acid. And so we get 10 to the minus 8 minus 25. That gives us 10 to the minus 33. Again, very unfavorable. Okay, I'm going to skip B. You can do that on your own and check with the key that's posted online. I'm going to move to C. And here's what I have, is I have two things that are neutral, so I don't have sodium to tell me which one is acid or which one is base. So they're both neutral. So what I need to do is the one that has the lower pKa will be acid. We have a pKa of 5 here for my carboxylic acid. And then here, the lowest pKa, because there's no H's on these ends, the lowest pKa I can find would be here or here, which would be 45. So that must mean that this is base. Okay, so this must be acid. And as we do this, to be a base, and I'd write this down, because I know I said it earlier, but you might not have write it down. To be a base, you must have lone pairs. To be a base, you must have lone pairs of electrons. Now, with that being said, both nitrogens have lone pairs of electrons. Well, localized electrons are more basic. Okay, this is because localized electrons cannot resonate, they cannot move, and therefore they're more inclined to react in an acid-base reaction. Okay, delocalized electrons, the electrons that can move, are a little bit more stabilized because they have resonance that helps stabilize them. So these electrons, these are delocalized. These ones are localized, and so this bottom nitrogen will actually end up being the nitrogen that reacts. I'm kind of curving my arrow here, which is a little bit strange, but that's what that would look like. The electrons go back to the adjacent oxygen. We get, and it takes a second to get these nitrogens drawn in. Plus this is conjugate base, this is conjugate acid. The conjugate acid, pKa, is about 11. It's a amine group that's positively charged. So we'll take 10 to the 11 minus 5. We get 10 to the 6. This is product favored because its K value is approximately 1 million. Okay, so there are 4 other practice problems below here that you can try out. These are old test questions. For example, in number 5, we see the same thing with localized versus delocalized electrons. That key is online. Please send me any questions that you may have over this.